Last time we talked about the atomic nucleus and how it consists of protons and neutrons, and it's a dense central point of the nucleus, and all the different notations, and what mass number and atomic number and all those things represented um, within an atom. So this time we're going to move on and talk a little bit about radioactive decay. So, what is radioactive decay? You can think of it as a property of an unstable nucleus. All right. And just quick review, if you remember, any given element on the periodic table can have many different isotopes. And we had used, for example, hydrogen 1, 2, and 3 as our example in the last video. So hydrogen 1, defined by its mass number, is a stable isotope. Hydrogen 2 is also a stable isotope. However, all of a sudden when you look at hydrogen 3, it is now considered an unstable isotope. So as a result of being unstable, hydrogen 3 is radioactive. Okay, so this kind of brings us into this first bullet point under here is some isotopes of an element may be stable, but chances are most isotopes for that any given element are going to be unstable, right? And as a result of them being unstable, they need to decay, meaning they need to change in one way or another in an effort to become more stable. So radioactive decay is the process by which an unstable atomic nuclei becomes more stable. Okay. And there's many different ways that can happen. The general idea is that the unstable nucleus is either going to ditch energy, ditch mass, reorganize itself, all in an effort to reach a greater stability. And that could involve changing into a completely different element altogether. So, how do we represent this, right? So, let's say we have an unstable nucleus, right? So, all right, unstable isotope that you're starting with. This is going to decay, which we call the decay mode, into something that is a new isotope. Okay, so it's going to decay into a new, more stable isotope. All right, so this is the general idea. This right here is the concept of a nuclear equation. So the idea that on one side you have your reactant. We'll leave that singular for now. And then on the other side here is the product of the decay. And products, we'll leave that plural for now. So now each of these things is going to have a mass number, right? Does not mean that each thing will have mass as we get into more detail. We also can include the atomic number for each of these things. Okay, so the reason I'm writing this out in this way, just to show you one thing. Essentially, the way these nuclear equations work is that the sum of one side, okay, so let's say we're looking at just the green here, the mass number, is equal to the sum of the mass numbers on the other side. All right. So if I take the mass number of my unstable isotope and I compare that to the combined mass number of the decay mode and the new isotope, those two things have to equal each other. All right. This is the idea. Basically, we are looking at the conservation of mass. All right. So conservation of mass and energy. Right. So both things apply here. Right. So no matter what you look at, that has to be true. You could do the same thing here looking at the atomic number. So the atomic number on this side, on the left side of the equation, has to equal the combined atomic numbers on the left side of the equation, on the right side, I mean. Okay, so you almost have to treat this as a couple different equations that you're solving in order to figure out how that isotope is changing depending on the type of decay. Okay, um, so let's look at this first one. Let's look at specific types of radioactive decay. Okay, and we're only going to cover a few of them. We're going to look at some of the easier ones. We are not going to cover all the different types of decay. So the first one let's talk about is beta minus decay. So beta minus happens when a neutron emits an electron. That electron can be represented as E negative, right? It's usually how we notate an electron, right? Um, as a result of it getting rid of negative charge, it's left with positive charge. So in the process, it's actually going to become a proton, right? And if you remember, protons, the number of protons an isotope or element has is known as its atomic number. So in this case, it's losing a neutron, but it's gaining a proton. So its mass isn't changing, but its atomic number is going up by one. So what does this look like? Well, let's take a look at carbon. Carbon, right? And we're specifically going to look at carbon 14, which has an atomic number of 6, is going to decay through beta minus, right? So this is our beta minus, which has a mass of 0 into nitrogen 14. Okay, 14. And if you look on the periodic table, nitrogen is number 7. Okay, so beta minus, why is it known as beta minus? Well, it's kicking out, it's emitting something that has a negative charge. So if you look at these atomic numbers, 6 has to equal some number plus 7. So a number -1 plus 7 would equal 6, right? 0 plus 14 on this right side is equal to 14 on the left side. So this is all balanced, right? The masses are equal on both sides of the equation, and the atomic numbers, when added on both sides of the equation, also equal each other. Okay, so this is the basic idea of what a nuclear equation is. So let's look at another example. So for example, if we have beta minus, that means you also have beta positive. So beta positive is a type of decay that happens when a proton emits positive charge, all right? So in this case, that would be known as a positron. And in the process of getting rid of some of its positive charge, it now becomes neutral, meaning you are left with a neutron. So a proton is changing into a neutron. So again, you're not actually kicking anything out of the nucleus besides charge. So as a result, its mass is going to stay the same again. So let's look at another isotope of carbon. In this case, let's look at carbon 10, which still has an atomic number of 6, right? Carbon 10 is going to undergo beta positive decay. So beta, which we know has a mass of 0, right? The beta particle is just charge, no mass, right? Um, and in this case, it is protons turning into a neutron. So its atomic number is going to go down by 1, and its mass is going to stay the same. So if you look at your periodic table and look for number 5, what you're going to find is boron. Okay. Um, and, well, a number plus 5 has to equal 6. So we know right down here in this case, this beta particle has a 1 here. So a positive 1 for beta positive, and a negative one for beta minus. Okay, so those are your two types of beta decay. So let's take a look at something a little bit different. What happens when a type of decay gets rid of mass? So, for example, in alpha decay, an isotope emits an alpha particle, right? Alpha particle consists of two protons and two neutrons, right? So it's basically eliminating a helium nucleus. So we could actually take this whole thing right here, and this is equal to a helium 4, right? Which has an atomic number of 2. We call it an alpha particle because it essentially, when it's emitted, has no electrons. So that alpha particle is a helium with a +2 charge. All right. When writing it out in a nuclear equation, just like what we did with the beta, we are going to refer to it as alpha particle. Okay. So yeah, it's essentially getting rid of two protons and two neutrons, right? And neutrons. Okay, so let's take a look at a specific example. So let's take uranium, right? Uranium is one of the larger and more radioactive substances on the periodic table. If we were to look at uranium, let's take a look at uranium 238. All right. Uranium has an atomic number of 92. So when uranium 238 undergoes alpha decay, it is going to be getting rid of that alpha particle, which has a mass of 4, an atomic number of 2, and is alpha, right? Plus. So what does this produce? Well, we know 4 plus a number has to equal 238. So if we just subtract across the arrow, right? So think of it as 238 minus 4, you will end up with a mass of 234. Okay. Now, if we take a look at the atomic number, well, we have to know 2 plus a number equals 92. So 92 minus 2 is just 90. And if you look on your periodic table for number 90, you will find the element thorium. All right. So uranium 238 undergoes alpha decay and decays into thorium 234. All right. So this is the basic premise of radioactive decay. Things we didn't discuss in this video is the concept of how unstable something might be and how you have other indicators of stability. So, for example, we talked a little bit last week about how do you calculate the average atomic mass of an isotope and how that atomic mass is weighted by the abundance of an isotope. So if an isotope is more stable, chances are that isotope is going to hang around for a longer period of time. You're going to accumulate it and it's going to have a higher abundance. So even though there are actually very few stable isotopes in the periodic table, the vast majority of matter that we know as it exists in those stable forms. While they move through the unstable forms relatively quickly, depending on the isotope. So you could almost look at it as the rate at which it decays could also be somewhat relatable to how stable it is. So if it decays at a very, very fast rate, that would imply that it is more unstable versus something that just takes a really long time to decay, might be considered slightly more stable. Although that might not necessarily always be the case. That's just kind of an overgeneralization. All right. So, basics of radioactive decay. If you have any questions, you know where to find us. Um, and that's it. Just take a stab at the homework and see how you do. All right, guys.